Hello, everyone. Welcome to the binary episode of the Day Zero podcast. I'm Spectre. With me is Z. Today we have an RCE in a Western Digital NAS, a NetGear bug, and a kernel race exploit strategy detailed by P0, and also a kernel exploit. So we'll get into some of those. First, though, we'll cover the Vuln solution for the week, and I'll let Z take that away.
In this week's Spot the Vuln was based off of one of the vulnerabilities from our bounty episode. And it really just, I simplified it a little bit from what the actual code looked like. The core issue in this one comes down to, or what it's trying to do first, is normalize the Unix path. So it takes a path in, looks for any of the ... slashes, and just tries to remove both that and the directory before it, effectively performing the directory traversal without actually needing to call it out to the operating system. The issue is that it is absolutely expecting there to be a directory named before that ... slash. So if you were to provide it a // ... it won't match that, and it'll basically let it through, allowing for a directory traversal later on in the code. This one core issue is just the fact that it's not matching on the ... slash, but expecting a little bit more because it's trying to be smart, and it's just outsmarted itself.
Yeah, basically stole the Vuln from yesterday's episode.
Yep.
But yeah. For those that didn't catch that episode, this is kind of a fun challenge working through the regular expression. So, all right, so we'll start off with our first topic here, which is an RCE in a Western Digital PR4100 NAS. Though the bug was in the NetTalk open source library for the Apple filing protocol, I believe, they just exploited it in the context of the Western Digital here, and that could be chained to get a pre-auth RCE on version 5.17.107, and likely on lower versions as well, though they didn't test that. They get into a good bit of background here on the AFP protocol and NetTalk specifically. The relevant bit from that for the vulnerability is an AFP. There's this concept of the Apple double file format, where metadata or extra attributes are stored in separate files to allow interoperability between file systems. So with that comes this idea of a fork file, where various different types of attributes can be stored in these fork files. So they list examples such as a data fork file for file data, a metadata fork file, and a resource fork file. So there's a command handler exposed for opening these fork files, which will then check its main header to see what type of file it is. The vulnerability is in the AD header read OSX function that gets called for parsing the resource file header. Basically, in this read function, they call parse entries to parse the header, which has a table of Apple double entries, which, like, what those are isn't super important for understanding the bug, but basically they're descriptors which have an ID and some backing data attached to it, like a file name or a directory ID or whatever. So each of these entries will have an offset and a length for that backing data, and the problem is, while parse entries will check for the offset and try to check if it would go out of bounds and return an error, and the return value of parse entries is technically checked in this AD header read OSX function, all they do is log a warning. They don't like fail or terminate execution or anything. They just continue using that offset, which eventually gets used for calculating the source and destination of a mem move, which gives you an out of bounds access. Furthermore, because the size is based on the entry length, which you also control the length of that copy, so you have a lot of influence over that mem move that's going on. Now, there are mitigations in play here. There is like NX, ASLR, and the binaries compiled as position independent. So even though this bug does give you a lot of powerful capabilities, it did take a little bit of work to abuse it. They observed that if they used a file that was small enough, I think they said under hex 1000 bytes, they were able to get the page where they would overflow from allocated hex C000 bytes away from the linking library, and they tried hitting the data segment and they got a crash when the AD open would eventually call this rebuild a double header function, which is used for writing back this a double structure into the mapped file, which gets saved to disk. The crash in this case, because basically they just like threw a payload in and wanted to see what would happen. The crash in this case was happening because the corruption they were performing was actually breaking the memmove function call. Because for those not familiar with memmove is kind of like an optimized memcopy, and it actually uses SSE. And SSE has some specific semantics and requirements that you have to respect. The data has to be aligned to a 16-byte boundary. So their overflow was misaligning that pointer, which would cause a panic, which got caught. And then later on, when it fell through down to the dynamic library to try to, I think it was doing like a lock call with the real time dynamic linking code. It would use a function pointer that ended up getting corrupted by their overflow. So they were actually getting code execution like right off the bat with that crash. But how they got there was a little bit interesting. Um, but when they started looking into that backtrace and figured out that ultimately they were getting there through the mem move, that then opened up the ability for them to get an info leak as well, because they had an attacker controlled offset with the stack pointer for the source of the mem move, so they could leak out of bounds stack contents, get it saved to a file, pull that file over Samba or whatever, and then exploit the bug again to do the same thing they did with the crash, but get it to call system or whatever. So yeah, kind of an interesting exploitation scenario. I thought the fact that they were using like the SSE violation there was pretty neat. I don't really think I've seen that used in an exploitation context like that before, but yeah, I mean their overflow here was a really powerful one because, like I said, they could control how far out of bounds they were going and the size of that. So, um, not too surprising they were able to take it to a full exploit here. And I guess we'll get into our next topic here, which is pretty similar, which is in NetGear. So this is another pre-auth RCE in the NetGear Nighthawk smart Wi-Fi router, specifically the R6700V3. This one sort of involves two vulnerabilities, though, chained together, unlike the last one. Z, I'll let you jump into this one.
I'll jump into that, but first I will also say thank you to Obfly for the 10 subs they just gifted out to the community. So everyone who got one of those, welcome in. As for this vulnerability, yeah, there are definitely some similarities with the other one that you just talked about. That said, it starts off fairly differently and requires a fairly privileged attacker. The first issue here is basically you've got the smart Wi-Fi router. It's going to be looking for updates, and how it does that is occasionally it's going to call out for this circleinfo.txt file. Comes from one of their web servers. And they probably just have like a cron running or whatever that just pulls that down every couple hours. Later on, the software itself will parse that file and basically check, is there an update? It has information like as a database checksum, version information from whatever. Kind of what you'd expect. Checks that, looking for differences. Problem being, it does that, and when it's building up the command line to actually download this file, one, it's using curl-k, which is basically saying, don't check the certificate. I don't care if it's valid. So even if they're using HTTPS, it really doesn't matter, because if somebody's in position to man in the middle of that, curl's just going to ignore it. Or is just going to ignore a bad cert. Which is kind of where the attack comes in. It does require an attacker that is able to take advantage of this issue. And that is, either in the network, DNS poisoning, something like that, in order to gain control over where this request is going. But they'll be able to exploit it, even though HTTPS is being used, simply because of using -k. So that's the core issue, or not the core issue, that's the kind of foothold that they use. The issue comes down into the software kind of expecting this to be more or less trusted data. So when they're parsing this file, you'll notice, for those of you watching, there's this db checksum, which just reads the hash into prepared, here it is, just a character array right on the stack, db checksum value. does that just using a straightforward scanf. So it reads a line, so it's going to be limited to 1024 bytes there as its reading line. Oddly, I just noticed it's reading 1000. Well, it's I just noticed the line's 1020, and then fgets is reading up to 1024.
Amazing. I missed that too.
Yeah, I just noticed it now, but the issue that was exploited was this scanf call. Basically, when you just use %s, there's no boundary check on that. There's no size check. It's just going to keep reading until it encounters a space for the rest of the word. So if you control that file, you control how much data is actually going to be read and thus written into these character arrays. So they can overflow both of them and actually overflow them by a fair amount. You've got the 256 buffer, so 700 and however many bytes left in that 1024 read is what you can overflow. This is on the stack. There's no stack canaries, so code execution at least was somewhat straightforward. At least getting that level of control on it. The control flow hijack. For actually exploiting this, what they went for was basically a one gadget style attack. So you just have this one piece of code that is sitting in the application code that ends up calling system and reading something off the stack. So it basically sets itself up with this system call and with since they control much of the stack at this point, they control much of the argument they control where the pointer at least is going to be heading into system. Little bit more complicated than that. The actual gadget that they found did like an addition. Yeah, here. Reading off the stack, doing a little calculation based off of R4, and then calling out the system. So a little bit more complicated, but essentially they have control over where the register is going to point, where the argument is, which means they just need to be able to point the calculated address to to some string that they control. On this system, while it didn't have full ASLR, there was system-wide the VA randomized VA space, right? That was set to 1, which is basically it's going to randomize shared libraries, the stack, but it won't be randomizing the location of the heap. That's just going to be after, I think it's code. Or not code. Anyway, it's not randomizing the heap's location. So it's relatively known. Of course, there are going to be different allocations or whatever. Effectively, all they need to do is brute force this, as it was just the case of. Also, I'll call out Belika in chat mentions that the buffer was 1024. Whoever reversed the code just made a typo. Completely possible there too.
That makes more sense.
It does. But yeah, coming back onto exploiting this, basically, with the heap not being completely randomized, obviously different allocations or whatever can toss it off a little bit, but they're going to be able to guess roughly where the heap's going to be, and they just need to find the specific address for something they control. Which they were basically able to do. One, they had their overflow, part of their payload here used... I don't know, it reminds me a little bit of just creating a NOP sled. Obviously, it's not a NOP sled exactly, but it reminded me of that, the old days of shell coding. Effectively, and this just comes down to how system works, they used a long string of A's as like a command name before their actual payload, which was like their actual exploit script. So basically, if the pointer that they passed into system landed anywhere inside of the set of 260 A's, it would read the rest of those A's out, see the semicolon, be like, hey, this command doesn't exist, and then keep going with the rest of their command. So kind of creating a little bit of a NOP sled in system, which I thought was a little bit of a fun trick there. Makes sense given what they're doing, because they just went basically for the brute force attack. They can get this reattempted every like 2 to 3 seconds. Brute forcing out the actual heap address. Eventually, it's going to land inside of their A's, and they get code execution from there. But yeah, I don't know. The thing I liked out of this one was really just that little bash NOP sled, basically.
Yeah, I just wanted to add on because I'm not sure. I think you might have skipped over it, but part of the reason they were able to use that magic gadget was because, unlike the Western Digital, they weren't using pi for this binary. So even though
Right, yeah.
ASLR was there, it was only partial. It wasn't, the code section was not randomized.
Yeah, I meant to mention that when I was going to the randomize VA space. Yeah, so they had the partial randomization for the actual global address space, shared libraries and stuff. Because it wasn't pi, the executables address space also wasn't done. And of course the heap. So the two areas that mattered, having gadgets for code and the heap, were both not sufficiently random.
Yeah, which does seem a little weird to me. Like, why would they go halfway on enabling like partial ASLR, but then not go all the way with enabling pi? Like, I don't know. Maybe there's some circumstance where, I can't even think of a circumstance where like compiling their binaries position independent would break anything. Like, it's 2022, so I don't know.
You would hope
It's a
not.
little
That
weird. Little
said,
weird.
randomized VA space, the default to that, I want to say, is it one or two now? I think it is two, so they would have actually need to step it back. I guess it also depends on what version of Linux they're actually running on this. So yeah, I think the modern default is two, so they would have also need to disable that in addition, like disable part of the ASLR in addition to not compiling with Pi.
Like you
Unless it
mentioned,
was
I think
performance reasons. Yeah,
it
Pi
could be.
Pi isn't default. I know that. That's Balika in chat mentioned. I think Pi isn't default on GCC. Yeah, Pi you need to
Yeah.
do the flag for it when you compile. Um, but for the actual system here, I think they would have need to back that down. So like it was definitely a design choice as to why they one didn't compile with Pi and two have ASLR set up this way. So if I had to make a guess, being a router limited system, probably along the lines of just performance reasons. Whether or not it's a legitimate performance reason is another discussion, but I could imagine that being the excuse.
Yeah. I was just trying to remember if Clang produced position independent code by default, because I remember there being a bit of a like back and forth on the LLVM forums that I saw. Like this was years ago, but they were talking about like the enable default pi flag, I think, and GCC had it, but Clang didn't. So I was trying to remember the nuances there, but um, I think that was a little bit of a different thing. So
Yeah, I'm not sure offhand if it does or not.
yeah, but yeah, I mean, both of these topics that we covered were pretty similar, just a different set of mitigations, and yeah, unfortunately for Netgear here, the router did not use very strong mitigations here. If they just had even like stack cookies, this might not have been exploitable, but they didn't. Though to be fair, the Western Digital, to my knowledge, didn't have stack cookies either. So yeah, we'll get into our last topic here, which is exploiting the ESP6 modules in the Linux kernel. So this is the ESP6 crypto module, which is apparently present and hittable on Ubuntu, Fedora, and Debian. I wasn't really familiar with it, so that was a cool bit of knowledge to pick up from here. And they were going to use this bug in Pwn to Own, but it got patched a few weeks ago, so that's why they posted this write up. The bug here is pretty straightforward as far as kernel bugs go. When receiving user messages, they use this SKB page frag refill function, which just allocates the static 8-page buffer, which gets allocated for the incoming data. But it's
Well, it
possible to
may
send,
allocate it. It can
yeah,
also
depending
just
on kernel
fill it.
config.
Yeah, basically, you ask it like, "Hey, do you have space for this thing?" You give it the alloc size. If it doesn't, all of its allocations will just be 8 pages because it's assuming it's going to need however much and doesn't want it. I mean, this is also the page allocator, not like kmalloc, so it is working a little bit at a bigger scale, basically.
Yeah, so I was just about to get into that. But yeah, that's a fair point with page refill. It will reallocate if needed, basically. Um, so yeah, because it will allocate this fixed 8-page buffer, but it's possible to send data that would exceed 8 pages in length. It'll just overflow. Now, where the bug is very straightforward, the exploitation is not, because like C said, this isn't like the heap overflows that we've covered in the past. This overflow isn't in a particular cache, but rather at the page level. So this post goes into some of the technical details of how the Linux kernel page allocator works for allocating backing pages for kmalloc caches. I don't want to go too deep into that here. You can read that in the post if it sounds interesting to you. Part of the reason I don't want to go into it is because it's kind of hard to talk about verbally. The diagrams are really helpful in the post for understanding this.
Yeah, you don't want to miss out on the animations here.
Yeah,
You
there
don't
was a
see
lot of effort put into them.
animations in these write-ups too often.
Yeah. Suffice it to say, for covering the bug, though, that the kmalloc 4K cache will ask for 8 pages of contiguous memory from the page allocator, which are known as order 3 pages. So you can perform some feng shui on the page allocator to corrupt adjacent pages, which are also order 3 pages, which are used for kmalloc 2K, 4K, and 8K. Now, there was a bit of work involved there. They had to mitigate the noise while shaping the heap, because there's a lot of other stuff going on under the hood. For example, like lower order pages can get consolidated into higher order pages or get split into lower level ones. There's a lot going on there. Their tricks involve like draining the free list of smaller caches and performing allocations in order 2 objects to try to reduce how much are getting borrowed. It's a bit difficult to go into audibly, but I think the diagrams in the write-up will be helpful for those who want to get more of the details on that level. Another thing that made exploitation a little bit more difficult here was when this overflow happened, there's this 8-byte trailer that's tacked onto the end that you don't have any control over. So if you're overflowing into an object and that 8 bytes happens to corrupt something that's critical, then you're kind of limited on your candidate objects because you obviously don't want to crash or something when you're trying to exploit it. They were able to use this though to derive an info leak as well as an arbitrary write to full chain it. The leak works by abusing the user key payload object from the add key syscall as a victim. Try to get it next to the overflow buffer and smash its data length field to then cause another out of bounds read to read an adjacent page filled with message objects. They set up these message objects so that the next pointers were filled with pointers to kmalloc 32, which I guess is something else I should get into a bit with the background here as well. Message is interesting in the Linux kernel in the way that if you send a message that's greater than 4048 bytes, it will store the excess data into like an auxiliary buffer it'll kmalloc or whatever, and then store that pointer in the next field. So by sending like a specially crafted message that was like 4050 bytes or whatever in size, they would be able to leak this message object in the kmalloc 4K cache, but then leak pointers to kmalloc 32. They then exploit the bug again to smash a message directly, corrupt the message text size, and set the next pointer to one of the ones they leaked, which then gives them an out of bounds read in kmalloc 32 cache. That was important because they use the sec operations object, which has function pointers to defeat KSLR, and that object is allocated in kmalloc 32. The arbitrary write was a little bit more straightforward than the leak, and here they used a previously documented technique from Will's root, which also used the message objects. Basically, calling back to what I was saying earlier, if you have that large message that exceeds 4048 bytes, it'll use the next pointer, which you can use as a corruption target to get an arbitrary write, because basically when it goes to load a message into that buffer, it'll do 2 copy from users. One into the initial message buffer, and then the second one into that next pointer. So if you can freeze that first copy using the userfault FD or fuse trick, then perform the exploit and swap out that next pointer for a pointer you control. Then when that second copy from user happens, you get an easy arbitrary write primitive. From there, it was pretty standard. They just use that to smash the mod probe path, which is another technique we've talked about before with other kernel exploits. But I think the leak was a lot more interesting here because we've talked about the idea of chaining primitives before. But we haven't, like with the Linux kernel, we haven't talked about going like 3 or 4 layers deep like that, because you're basically having to go from like a page level leak or out of bounds read to a kmalloc 32 out of bounds read. So how they crossed that bridge was really interesting to me, just kind of abusing the message object to cross that boundary. Um, but yeah, there's a lot of like cool heap internals here for the Linux kernel that are really useful to know even outside of this exploit. And like Z said, the diagrams are super helpful and well done as well.
Yeah, all around, it's a well done post. Just in terms of readability, flow, and animations. Gotta give credit for the animations. Um, I will say, like, in terms of the exploitation, I mean, yes, we focused a lot, like, this is all Linux structures, but this concept definitely applies elsewhere, too. I mean, corrupting data length is something we have seen done. I mean, maybe not that specific structure in that specific field, but the idea of corrupting a data length is pretty powerful when it comes to trying to chain the primitives. When you corrupt a length, you're often able to gain another, like a read or a write or both primitives out of it, and that's kind of what we see here. So, I mean, it is a little bit, it is Linux specific, but at the same time, I think conceptually a lot of this applies to other sorts of exploitation too.
For sure. This has a bit more of a browser-esque feel to it than some of the other kernel exploits we've covered. I've kind of said in the past that browser, I think, is harder in terms of exploitation than kernel is. You typically have more layers of abstraction going on, you're chaining more primitives, and this is a little bit more akin to what you would see in browser exploitation, so that was kind of neat. But yeah, like you said, this is very applicable to other targets as well, but there's also a lot of info here, like if you're just looking at Linux, that will be very useful to you. So
Yeah.
um, yeah, all around good resource for anybody out there that's doing binary exploitation
Yeah,
or
great
memory
post.
corruption.
I wish they posted more. Looks like this was their first post this year and they only did like one last year.
Yeah. So we do have one shout out this week, which goes a little bit more into the specifics of Linux. This is another Linux kernel based topic, and it's from Project Zero, and it's called "Racing Against the Clock: Hitting a Tiny Kernel Race Window." Um, the article is kind of what the title would suggest. It talks about trying to hit really tight race conditions and some tricks you can use to like widen the race window, using things like cache misses and stuff like that. Unlike the last topic, a lot of this I think will be pretty specific to Linux. I don't really know how much of this you can transfer to other targets. When you start getting into concurrency and stuff, the kernel is kind of unique in the amount of influence that you have over like what the scheduler is doing and whatnot, and over like memory accesses. But still, I took a quick glance through this post, and there are some cool tricks in here that I like totally wasn't aware of. So we wanted to give it a bit of a shout out. It does go pretty deep into like the cache level and the interrupt level, with because basically their tricks involve like using high resolution timers to try to get an interrupt fired inside of a race window to process a bunch of events or something like that, or like abuse cache misses to try to get memory accesses to take longer. So it does go a little bit like under the hood of what you might be familiar with, because I know at least me for a long time, like a lot of this stuff with like interrupts and memory accesses, I just kind of glanced over it and treated it as a black box because it can get really confusing and really complex really quickly. But yeah, I mean that's part of why this post is so valuable, is it gives you that insight into those lower level semantics that are going on and how you can take advantage of them in race condition scenarios. So cool post, but it's a little bit too specific to Linux for us to like cover fully in depth. And also it's abusing an older bug. It's mostly just like a bunch of tricks. So
Yeah,
wanted to shout it out.
I'll also just shout out, since you just mentioned that it's a tight race window. I mean, this is a 12 instruction long race window. Very tight. I mean, a lot tighter than what most race windows, even what we'd call a short race window, is. 12 instructions. I mean, that's the only time I think we've talked about the instruction count and relative to races with less was, I think, when we were doing the speculative race Yeah, speculative use after freeze, where they only had like a 6 window, but I mean, that's a little bit different because that was the window that they had of speculation. But I mean, yeah, 12 instructions is not a lot of time.
Unfortunately, I can say personally, I've found race condition bugs that had an even tighter window than this. The race window I remember was like literally 2 instructions. Uh,
Well, there you
Needless
go.
to say, I wrote that down as not exploitable and I moved on. I didn't even really put a lot of time into that because that's insane. But yeah, like even how many did you say? Yeah, 12 instructions. Even 12 instructions like that is insanely small when you're especially when you're talking about modern processors and all the optimizations and stuff they have to fly through instructions. So um, yeah, widening the window is necessary here to get a reliable exploit. So the tricks were definitely necessary. And I've always just loved those kinds of tricks. Like, this kind of reminded me of some of the older, more well-known tricks that I know of. Like, for example, like when you try to get data laid across pages inside of a race window, so that when it goes to read or write to that, um, it crosses a page boundary, which takes longer on the memory access side of things. That's kind of what's going on here, but more like low level. So. Uh, I also noticed they did some testing between different CPUs, which I thought was kind of interesting. Like they mentioned the like Tiger Lake and some of the other CPUs they tested against, just to see like how the behavior differed. I didn't read too much into that, but there's some interesting statistics information there too. They got some graphs and whatnot. So yeah, there's a lot in that post, as is usual with Project Zero. All right, but yeah. Do you have anything else you want to add on to the P0 post or any other posty, or
Yeah, and
if
no, I
not, we'll
don't,
wrap it up.
and no shout out, no other shout outs.
All right, cool. So we'll wrap it up there. Thank you everyone who tuned in. The VOD will be up on YouTube and Spotify and other platforms tomorrow. Feel free to follow our Twitter and join our Discord to join the community. We'll be back next week on Monday and Tuesday for the Bounty and Binary episodes respectively, and we'll see you all then.